if you think of the measurements the way the measurements were done of frequency of different frequencies in the past, they were done using frequency chains. I'm showing a diagram of NRC frequency chain on the left-hand side, and this was a extremely complex experiment that involved multiple lasers and frequency mixing. It took years to build, weeks to align by several persons, and it ran for about 20 minutes at a time. Still, it allowed the measurement of strontium ion frequency transition in 99 with accuracy of 5 × 10⁻13. Nowadays, you have frequency combs, which are commonly commercial. Nowadays can be commercial combs. And this is the picture on the right, and this diagram is from a frequency comb optical comparison measurement set up at the National Physics Lab in UK. This is the Metrology Institute at NPL. And so you have one frequency comb that has multiple output arms. Each one of these arms is amplified for specific output frequency to maximize the output frequency at one specific wavelength. And this is these different arms of the frequency comb can be used to measure clock laser frequency that are used for different optical clocks. And here you have example of 1, 2, 3, 4 clocks that operate simultaneously with the same flywheel, with the same frequency comb. The advantage is that you can compare the frequency of these clocks directly, even though their clock lasers are at different wavelengths through the comb. And you only require one really ultra-stable clock laser, which is required for clock operations, because you can transfer the stability of that ultra-stable laser to all the other probe lasers, again, through the frequency comb. If you lock the comb to that specific ultra-stable lasers, the other lines will benefit immediately from the stability. And nowadays, the stability of the combs, the measurements with the combs, reaches levels at the 10 to minus, better than 10 to minus 18, 10 to minus 19. And that allows now to use optical frequency standards to measure absolute frequency values. And this is the technology that really enables the upcoming. Sorry, somebody is not on mute. And this is really the technology that allows now to prepare for the transition between microwave definition of optical frequency, which is currently defined using a cesium atom, to an optical frequency transition, which would allow in turn the increased accuracy in the realization of SI second. Now it's limited the few parts, low parts 10 to minus 16. With optical clocks, it will be few parts 10 to minus 18. The combs we operate at NRC and Metrology Research Center. There are two combs that we operate regularly. The Thai sapphire comb, that's on the left-hand side, the Thai sapphire comb and the fiber comb based on the erbium doped fiber. And they're used for laser calibrations of client lasers and wave meters, also for calibration of lasers for dimensional metrology, and therefore the realization of the meter, and also for measurement of the frequency of our optical single trapped strontium ion frequency standard. On the square on the right-hand side of the slide, you see an image of new frequency combs that are under construction right now at NRC. And they also Thai sapphire combs and erbium doped fiber, but they have different design, different size, and promise much better stability and accuracy. And the Thai sapphire comb actually generates the supercontinuum directly in the oscillator, so you don't need an extra amplifier arm to generate the supercontinuum, which simplifies the design of the system. So the combs, as I mentioned, they have a wide spectral range, and here I'm showing the 3 different types of combs: the erbium combs, fiber combs, the ytterbium also fiber combs, but just a different amplification medium. They have a different spectrum, and the Ti-sapphire combs, and they provide the spectrum coverage to allow comparisons between measurements of different optical frequency standards. And you see examples here shown on the graph. But and this optical frequency standards will be the basis for the new definition of the SI second, as I mentioned, and this will happen in the next 5 to 10 years. But the measurement of time, measurement of frequency, is moving forward, and the research into development of clocks based on nuclear transitions is already ongoing. And here on the right-hand side, I'm showing the wavelength for the thorium nuclear clock, which wavelength has been recently measured to be around 149.7 nanometers. And in order to actually build the clock, one would need to have a comb that operates in the same wavelength to allow the transfer of clock stability to microwave and to RF frequencies that are used in regular instruments operations. To build the clock, you need to transfer the stability of very high frequency to the radio frequency, and this individual in hertz as well. So the nuclear clock promises stability, promises accuracy and stability at the level of 10 to minus 19, and it will be the next definition of the SI second, probably in the 20 years time scale. But what do we need for that? We need a comb at VUV spectral range. And how can it be generated? It can be generated with high harmonics, and how Paul will be talking about it. But if we have a comb at VUV, we can not only use it for nuclear clocks, but it can be used for XUV spectroscopy, material band structure measurements, and non-invasive electronic currents detection, just expanding the reach of the combs uses. They used as infrared combs that invisible are used right now to the new domain. And in our work, we will be leveraging resources of and know-how from labs around the world, because this is not a new idea. People are thinking about VUV combs. They built some at NIST and JILA. The microstructures on titanium nitride microstructures from expertise is in our collaboration with Purdue University. And the nuclear frequency standards are the one that are using VUV light and would need the combs. This is the Metrology Institute in Germany, PTB. And now I'm transferring my presentation to Paul. Thank you.
Okay, can everybody hear me? I think I'm unmuted now, but I'm not at the top of my presentation, so let me go out. So in 2005, the year the Nobel Prize was awarded for the frequency comb, the first high harmonic frequency comb was made. You heard about the frequency comb. Let me get the pointer here. There's the laser pointer. You heard about the frequency comb from Marina, and the frequency comb that she just described sits here in this figure. This figure shows a high harmonic frequency comb, first operated in 2005. The remainder is the high harmonic part of the frequency comb, the conversion of the frequency comb from the frequencies in the visible or near infrared to the XUV. Currently, this can operate up to 100 electron volts. In other words, we can transfer the stability of the frequency comb that you heard about before to up to about 100 electron volts and photon energy. However, the process by which it's done is reasonably complex, as you can see here. What is essential is that one takes the radiation from the current comb and places it up in a build-up cavity, shown down here, and that build-up cavity must have exactly the same mode separation, mode spacing, as in the oscillator that's feeding the cavity. And if it does, that requires great stability, both mode matching in space and in frequency. If it does, the radiation intensity builds up in this build-up cavity by factors of 10, 100, or even more. And that's sufficient to create high harmonics created down here in the xenon jet inside the system. While complex, this is the best way to get a frequency standard in the VUV and the soft X-ray region. And by now, people like Tom Allison would say, this is the best way to do photoelectron spectroscopy in the VUV. 3 years later, there was a paper published in Nature. Many people saw this paper, and it was a paper describing the potential of using small resonant antennas to resonate with the radiation coming in and increase the field, not by building it up in a cavity, but building it up by resonant on a small nanostructure. These nanostructures you can see here or illustrated over on the left-hand side of the figure were resonant with the driving laser frequency, which was Ti sapphire. And the paper described creating high harmonics from this resonator with a gas in between. Actually, I was one of the reviewers in this paper. I know some of the other reviewers as well. I asked a number of questions before I let the paper go through. Of course, it went through and it was published. And one of the things I was worried about was there enough gas molecules, or gas atoms rather, in order to really break down and give us radiation? I thought perhaps some condensed, because I think they were using condensed on the surface. And in the end, I let it go through. But over time, it's turned out that this was not correctly observed or correctly interpreted, perhaps I should say. The nanoplasmonic resonance was there. There's an enhancement of the field, just like expected. But the radiation that was seen was not harmonic radiation. It was incoherent radiation from the source. So while the idea was clear and the idea was correct, the radiation, the result was incorrect. That was 3 years later than the original frequency comb, and this was an effort to bypass it. 3 years later still, Shambhu Gamir, working in Ohio State, began to look at solids. And he found, and that group found, that using zinc oxide as a solid instead of a gas, they could find a series of harmonics of the drive-in laser frequency, in that case 3.5 microns, a series of harmonics spaced equally and extending out, much like you saw from a gas phase process. It seemed eerily like high harmonics from gas phase. This found in solids. This was 20, 30 years from gases, and it's amazing it would be missed all during that time. Now in solids, we often think in energy and momentum space. And so I have on the left hand the atomic case, but shown in energy and momentum space. Here is a horizontal line looking at the energy and momentum of the ion, one of the things like the hole created when you ionize an atom. And here on the upper curve, you see the electron, a parabolic curve, showing the energy versus momentum of the electron. Ionization creates an electron and hole. They're both accelerated in the field. They move around until they find each other in physical space, and they recombine, giving off a photon, which is the high harmonic photon that we see. In fact, we know that there are two sources of high harmonics, but the other one, which we locally often call Brinell harmonics, he was a scientist here in NRC and thought about these kind of harmonics quite a bit, is a second case, not so important in gases, but in semiconductors, both of these are in principle important. In fact, the original paper by Gamir, they felt that it was the Brinell harmonics, or the analog of Brinell harmonics in solids, that was the primary source of the harmonics. But work here by Thomas Brabitz and Giulio Vampa, who was then a student of mine, currently at Stanford, but eventually coming back to NRC, began looking at solids and began to realize that really the ideas from a gas transferred almost perfectly to a solid. They published a paper, and 3 years later again, in 2014, and the key experiments were done in 2015, both performed at the University of Ottawa and NRC. So it was clear immediately that maybe we could get around the problem of frequency combs by using solids and make them, simplify them greatly. So there are many things that one might try to do, and immediately we tried one thing. Kevin Lee, a former student of mine, PhD student who is now at IMRA, had developed a thulium laser operating at 2 microns. It operated at 100 megahertz. And so we said, let's see if we can take some of these semiconductors and just place it in front of the thulium laser. This is a very simple experiment. The beam comes in, mode-locked thulium laser beam, focused into the target, and the target was zinc oxide or silicon, and both work fine. Now, my own personal view was we would melt the silicon or zinc oxide and we'd have a puddle in the bottom, but we decided to try the most simple thing we could do. We focused the beam through, picked up the harmonics, took them through a piece of calcium fluoride prism, and lo and behold, we found harmonics. We found harmonics that were affected by heating, correct? But still, they were clearly there in a CW basis. We could make, in principle, a frequency comb at 100 megahertz. Heat dissipation will likely be a problem, but on the other hand, a frequency comb probably could be made. We could run harmonics at 100 megahertz. So that was a big step. In fact, Giulio Vampa, who worked on that as well, the Giulio that you heard before, went on to look at these, again, directly pumped with a 2 micron laser, a different 2 micron laser, and showed that this work was done in Stanford, showed that you can go up to the full band differential in zinc oxide and have 11 EV harmonics. 11 EV would cover this nuclear transition that Marina just talked about. So looks good. So now let's ask about nanoplasmonics. Nanoplasmonics allow us to lower the intensity to use this resonance. And so we decided to try that too. So there we brought in Pierre Barini. Pierre Barini is a electrical engineer at the University of Ottawa who runs a nanofabrication facility and is an expert in nanoplasmonics. And we discussed with him how to do it. And he suggested a very simple design. Up here, you see a nanoplasmonic antennas. The dimensions are here. You can see them on the side. The dimensions are written on the figure. And they're simple dipole antenna, which oscillates when I bring radiation onto it and increases the field of 2 microns, designed for 2 microns, increases the 2 micron field by an order of magnitude or 2. If it's resonant in this direction, and if it's not in that direction, which would not be resonant, of course, the enhancement is not there. These antennas were laid out in an array that's a square. You can see the square here, and you can see the enhancement is present there. It's an enhancement about 10 times if you change the polarization from one side and the other. In the left, we have the enhancement. On the right-hand figure, we have no enhancement, perpendicular polarization. These are gold antennas in silicon, resonant for 2 microns. The signal averaged over the full surface is a factor of 10 enhancement. But of course, if you were trying to say, where was the enhancement? It's really close to the antenna. The enhancement was probably between 2,500 and 10,000 due to the antenna. So now we know that this idea of building a small resonant antenna also works. Of course, gold is not very good. gold melts, we melted the gold antennas. We couldn't drive these as hard as we might have liked, but again, we've shown another concept that nanoplasmonics can work and can work so next, the final one, you might say, is how far can we go? And the best material, as far as I know, is MgO. With MgO, you can reach about 30 eV, the shortest wavelength, I think, for solid state harmonics at the present. MgO covers a great deal of the region that you need for photoelectron spectroscopy. MgO covers the nuclear transition that Marina mentioned in thulium ion, and that transition will probably be the long-term clock. In fact, in that paper, I have a quote from that paper, the energy transition between the ground state and the first excited state corresponds to a wavelength of 149.7 meters, which is accessible by laser spectroscopy through high harmonic generation. And that the reference is there. And so it's clear that we have an aim, a way to get there, and then how do you get there? Well, that's what Alexei's going to talk about. So Alexei is a postdoc working on this. I want 2 more slides, so I want to just highlight quickly what he's going to say or he has accomplished. We can reach, as I mentioned to you before, in MgO harmonics greater than 25 VV at intensities on the order of 10 to the 13 watts per square centimeter. Using a counter-propagating configuration, Alexei has shown that there is a significantly increased efficiency. We can probably get to an optimum efficiency in this way. Using total internal reflection configuration, we have designed a system which we think will be easy and efficient and able to get high harmonics outside. So that's the substrate. Now what about antennas? Can we bring down the intensity? Can we make these really, really, really simple devices? Well, we have to do something about the damage problem, and the most likely material is titanium nitride. It's really a high, robust material. It's plasmonic in nature. And so we've set up a collaboration with the Purdue group to get titanium nitride. It's lattice-matched MgO. And we've now found that it can withstand intensities of greater than 10 to the 13 watts per square centimeter. This is orders of magnitude more than gold. And we observed, in fact, high harmonics from titanium nitride. I believe the first observation of high harmonics from a metal. And now, before I pass on to Alexei, I know it's important for NRC to talk about collaboration. So let me just end with collaborations and then we'll go to the detailed research. So I have a long-term collaboration with Zhenghu Cheng at the University of Central Florida. This has gone on over a number of years through MURIs, through DARPA grants, and now we have a DTRA grant, that's Defense Threat in the US. It's a well-funded grant, and it's for looking at nanoplasmonic antennas or nanoplasmonic structures to deal with harmonics that go up to quite a short wavelength. And can we find an efficient way to create these harmonics? So that's a clear overlap with what we're doing here. Of course, we could not move into titanium nitride, especially lattice-matched titanium nitride grown in MgO without going to Vlad Chilayev. I believe he is the world expert in this. And so we've set up a collaboration with Purdue, the first time we've done this. So this is a new collaboration, really growing from this project. And we are aimed to see what are the limits of titanium nitride. How far can we push it? Can we really make devices out of it? I told you we found titanium nitride harmonics, and Laura Ramuno is asked for, and we've sent her all the information on titanium nitride, both our harmonics and all the characteristics we know of titanium nitride. And she's starting to look at theory of harmonic generation from titanium nitride, as we have, but as experimentalists, she will have with as a great theorist. And I mentioned the long-term collaboration we've had with Pierre Barini on everything to do with nanofabrication at the University of Ottawa, and that collaboration continues. And he's sort of been behind the scenes, talking over my shoulder, telling me that Vlad Chilayev is really good. This is a place to go for titanium nitride. and giving constant advice and helping on this, and just being a great collaborator. So now I'll pass this on to Alexei, and Alexei will finish us off with the details. And stop sharing.
Thank you, Paul. Okay, can you hear? Can you see my screen? Can you hear me nice?
Yes, I can see your screen, your full screen.
Okay, good. So I'm going to talk about a few of our experimental results related to the project and some plans for the following experiments. As you learned from Paul's talk, a wideband dielectric such as MGO can be used to generate vacuum ultraviolet radiation. One would require really high intensities for that, although of order of 10 terawatt per square centimeter and higher. The emitted vacuum ultraviolet readily absorbs and reabsorbs, and the typical absorption length is of order of from 1 to a few tenths of nanometers. That means that the only a thin layer on the output interface usually participates in the emission that is not reabsorbed, like shown here. The rest of the bulk not only not helping in the emission of this radiation, but also in fact makes things worse by introducing nonlinear propagation phase on the fundamental, which later gets inherited by the emitted harmonics. A similar estimate shown here, for example, of a Kerr effect shows that at intensity as low as 5 terawatts per square centimeter for a 200 micron thick sample, one would already have substantial modification of a spatial phase. For example, I'm sorry, I have to restart my animation. Doesn't work. Give me a sec. Sorry about that. Okay, share screen. Yeah, as can be seen of this recorded far field profiles of the generated VUV harmonics from MGO, the special profile, the special properties degrade really quickly with the driving field intensity, especially for thicker samples. What that means is that it is desired that this required high intensity of the laser field is concentrated exactly at the interface where the harmonics are generated. So one approach that we demonstrated to do this concentration of energy is using two counter-propagating pulses to simultaneously illuminate the output surface of the sample from two sides. The two pulses interfere to produce a fully partial, depending on the ratio of the amplitudes of the pulses, staging wave. And carefully tuning the delay between the two pulses, we can put anti-node of the electric field exactly on the interface. And this allows us to concentrate the peak intensity to a thin, few micron thick layer of material close to the output interface, whereas the bulk only experiences a quarter of this intensity for the same peak field amplitude. So here's the experimental setup that we used for this experiment. We used 2 concave mirrors to focus 2 nearly identical counter-propagating pulses on the output interface of a 200 micron thick MgO single crystal shown here inside a vacuum chamber. The normal of the sample was aligned along the bisect between the directions of the two beams. This way, the field anti-node planes were parallel to the surface of the sample. The generated VUV hit either the slit of a VUV spectrometer or was bounced off the floating mirror and hit the imaging CV detector directly. In this movie, which I'm going to start in a sec, the measured far field profile of the XCV is shown as we vary the delay of the between the 2 pulses. And note this, it's a logarithmic scale, and you see as the pulses start overlapping on the output surface, you see very deep oscillation of a high signal of with the modulation depth of around 2 orders of magnitude. As this happens as the interface passes nodes and antinodes of the resulting standing wave. We then fix our delay at the constructive so that the pulses interfere constructively on the interface, and we switch to a spectrally resolved measurement. Now pay attention to the top row only for now. We see harmonics 5 to 15 observed for the chosen combination of the intensities of the 2 pulses. Note that the intensity of forward propagating pulse was chosen really low, so that no propagation effect plays any role, whereas the majority of energy was taken from just the backward propagating pulse. We compared the harmonics generated this way to the harmonics generated by single backward propagating beam, and we chose its intensity so that the peak field amplitude was the same near the output interface. In fact, it had to be twice the total intensity of the field due to interference in the constructive addition of the first 2. We found that the spectrum generated with a single beam was had the same spectral shape and similar cutoff, and it was slightly less diverging in the far field, but we observed that it was that our method gave a 3 to 4-fold increase in the despite using only half of the pulse energy. A few fold increase in the space integrated harmonic yield, which we can see here, where a single beam shown in blue compared to the counter-propagating beam shown in red. Again, it's the same peak field amplitude. Can be attributed to phase matching. One can think of it the following way: if we only have backward propagating beam and generated harmonics, they propagate in the opposite direction, which means that the phase mismatch between the 2 is accumulated very quickly. But having generating field as a standing wave, or at least partially standing wave, it allows us to decrease the phase mismatch and increase the harmonic generation efficiency. as qualitatively described by the dashed curve. So having those two non-collinear beams space and time overlapped on the sample surface can be not that practical. So we were looking at a better approach of doing this thing. And a better approach might be using a tapered sample so that as shown here, so that the input beam penetrates through the sample and then totally internally reflects from the output surface. As can be seen from the Fresnel equation, let's say RS reflection amplitude coefficient of reflection, it reaches 1 when the angle of incidence reaches the critical angle, +1. According to the convention for this, that means that the field on the interface and the reflected wave looks in the same direction as the incoming wave. That means that the field would have an antinode on the field exactly on the interface, and that's exactly what we need for counterpropagating configuration. However, there is a complication. So to demonstrate it, I'll explain how a total inflection works simply in terms of k vector. As the light beam refracts through a planar interface, its wave vector projection onto the interface is k parallel in material is conserved. So when this value becomes larger than the absolute value of the total vector k vector in the vacuum, this conservation law cannot be satisfied, and therefore nothing actually refracts. Everything is reflecting. But if that holds, which holds for total internal reflection case, then also this equation holds, which I got from the bottom one by just multiplying by n, where n is the number as a harmonic order. So what it means that if you can't satisfy, if the total internal reflection condition satisfied for fundamental, it's also necessarily satisfied for harmonic, for any harmonic. To overcome that, we can actually write a grating or machine a grating on the surface of the sample, and so now this conservation only has to hold up to a wave vector of this grating g, the spatial frequency g. But now, if the period of the grating is small enough, or equivalently g is large enough, we can make it so that the condition of being able to propagate is satisfied for nth harmonic, but not for fundamental. As you would expect, too frequent of a grating would do nothing, can do nothing to long wavelength radiation. So here I plot some frequency domain finite difference time domain calculation, the Maxwell equation solution to the laser pulse incoming at a 40-degree angle from inside the MGO to the vacuum boundary, and totally internally reflecting and going back down. And the sample boundary, the sample actually is shown in gray, you can see here maybe, and it has this grating on top. And you can see the grating does not affect it much, it just reflects, and there's this there's some periodic structure which is just fringes because of the interference of the incoming and reflected beams, and there is also some evanescence field which doesn't propagate further than say a wavelength or so. But what's interesting shown here is I also plot surfaces of constant phase, and I plot them every 2 pi over 11, and you can see if your structure is aligned perfectly with that. That means that 11th harmonic would be actually emitted in the direction exactly normal to the surface. Now, this method, in addition to the advantages of the counter-propagating beam configuration discussed above, that we able to concentrate the field exactly at the interface. This also allows us to separate VUV radiation from very intense laser field. One little development of this idea is that the grating doesn't have to be straight. In fact, we can machine it curved, so the phase that we write on this on the generated XCV is not a plane wave, but rather a focused beam. And since this focus can be arbitrarily close to the surface of the wavelength, we can hope to achieve really tight focusing the fundamental can you hear me?
Yeah, your audio was breaking up, Alexei. We've lost your screen now. At least your video is moving. Do you want to try to share your screen again?
Yeah. So the first calculation, so it can provide a very useful tool for very tightly focused XCV harmonics in the absence of fundamental three focused XCV, and we did some initial calculations, and we show that we can probably do it. And the reason why this could be important is that in principle we can use it for specially resolved mass spectrometry and laser machining, where the XCV, tightly focused XCV, used to inject electrons in a tiny volume, when and the IR field loosely focused, then drive them around and destroy the material only in a very small volume. And this is done in collaboration with Pierre Birini, who are currently in the process of manufacturing those for samples. But now let me go back to the plasmonics and talk about the alternative approach of concentrating the fields and the interface. So we can place plasmonic non-antenna on top of the dielectric, as was shown in the Julius paper that Paul was talking about. And if we pump it with resonant wavelengths, we get an enhancement. The one problem with this approach, as Paul already mentioned, is the low damage threshold of the typical plasmonic metals, and for example, gold, that's sort of like one of the most common plasmonic materials, has a damage threshold for lasers at around 1 terawatt per square centimeter range. And to remind you, we need 10 or more. So a possible solution to this problem is the use of the novel plasmonic materials, refractory metals, such as titanium nitride. So this is a very robust material. They use it for tool coating. And in this plot, like popular plasmonic materials are summarized comparing the crossover wavelength as the wavelength starting from which they exhibit plasmonic properties. Imaginary part of permittivity, which stands for losses, and also bulk melting point. And here you can see titanium nitride here compared against gold and silver, and you see that it's comparable in crossover wavelength and imaginary part of permittivity, but it has twice higher bulk melting point, which is prominent and which is promising. So we collaborate with, as Paul already mentioned, with Vladimir Shalayev group in Purdue, who can produce this single crystal TIN film of very high quality and make plasmonic devices with them. And coincidentally, to our benefit, TIN is extremely sensitive, extremely similar to MgO in terms of lattice structure. It actually has also a rock solid structure with a similar lattice constant, and they can be lattice matched, and they can be grown directly on MgO. So we've got the 200 nanometer TIN films grown on MgO substrate, and we start by studying the damage threshold. We focus 6 femtosecond 800 nanometer wavelength laser pulse onto TIN covered side of the substrate, like shown here, and the sample was mounted on a motorized stage. We tested a range of peak intensities, and at each intensity we irradiated the sample for a minute, and then moved the sample to a new spot. The sample was then studied under optical microscope, and here you can see the image acquired with frontal illumination. Visible damage was observed at intensities of 14 terawatts per square centimeter and higher. And at the intensity of 17 and higher, the sample looked like the TIN was stripped completely off, leaving a clear MgO behind. This is more evident in the back illumination, where you can see through the sample after 17 terawatts or so. So now we overlapped the measured beam profile at different pulse intensities shown with wire grid 3D plot, and with our microscope images, and this way we determined the peak damage intensity to be at 13.4 terawatts per square centimeter. So for comparison, here I show the MgO spectrum taken at this at the very same intensity, and harmonics up to 16 eV or so are observed. As Paul mentioned, there are two common mechanisms of high harmonics in solids, and dominant in dielectrics is this interband mechanism, where which is recollision essentially. Strong field excites electron hole pairs, drive them around, and then they recombine, releasing the energy excess as in form of XUV photon. But in metals, one can expand also strong intra-band contribution. So there are a lot of electrons already in the conduction band, and if you just drive them around in non-parabolic band, there would be nonlinear currents associated, and you can emit harmonics this way. But low damage threshold usually prevents from reaching this non-quadratic regions of the band where this nonlinear effects becomes high enough to be observed. But high damage threshold of TIN suggests the possibility that we maybe can do that in TIN. So we used pretty much similar setup as before, just eliminating it from the TIN side, and in the specular direction, we had an XUV spectrometer with a slit and grating, and also the TIN sample that we used had a border of a few millimeters thick, free of TIN. That was bare MGO, and that provided us with a nice reference from MGO, from harmonics from bare MGO without needing to realign anything. So the top plot here shows the harmonics for MGO and TIN at the range of intensities from up to 15 teras per centimeter. And for TIN, in fact, harmonics 5 and 7 were detected. And different shape of the spectra points to different nature of the different origin of the harmonics, and so does different intensity scaling shown here. So solid lines for TIN and dashed lines for MGO. And one can also notice that this is arbitrary units, but it's the same scale for all depicted curves. So one can see that the detected harmonics intensity was comparable from bare MGO and from TIN at the same intensity that the TIN was able to withstand. So that's just possibility maybe to use TIN as a generating. So TIN is both a plasmonic device and to enhance the field, but also to generate harmonics right on it. We also performed some angular scans. We can change the polarization of the driving field and see the efficiency of the generated harmonics. And for all used intensities and for both harmonics, we found it to be really strongly peaked for driving fields along gamma X direction. To try to model the system, we performed some DFT calculations and to find TIN band energies and velocities. We found 3 conduction bands, color-coded here by blue, green, and red. One thing that should be noted here is that in dielectrics, the electrons are usually injected close to a single point where the band gap is the smallest, and then they just follow electric fields, and that's why you can often get away with just 1D calculations. You just find the band structure in the direction that, or band energies in the direction that the field drives the electrons. Here, since the electrons initially occupy like a large portion of the Brillouin zone, we actually need the full 3D calculations, and that's what we did. So here is the Fermi surfaces for the 3 bands I mentioned using the same color scheme, and one band, the blue one, actually has like the absolute majority of the electron of the populated states, and in fact it contributes the most to the harmonic currents. Sorry, to nonlinear currents, and actually that's what creates harmonics. So in our simple model, we now make all these populated states within this blue cross follow the electric field, and for each shift of this populated states, we can integrate over Brilliant zone and find the total velocity, and that would be our current. And that's what we did. And in these two plots, I compare the measured showed in dashed lines and calculated solid lines, intensity scaling on the left, and the angular dependence for the two harmonics. And the calculated intensity scaling demonstrates some non-monotonic behavior, and that we don't see experimentally, but the angular plots do capture the observed anisotropy. And we are currently, as Paul mentioned, collaborating with Laura Moon group for more involved theoretical treatment of the system. And with that, thank you for your attention.
Okay, thanks, Alexei. So now, if anybody has questions, turn on your camera and unmute your microphone, and let's see what we've got.
I have a question. So titanium nitrides are correlated metal, am I correct?
What is that, sorry?
They are correlated metal, am I correct? So there are strong electron-electron interactions am I correct?
I'm not sure about that. No,
because when people look at, they say there is a strong electron-electron interaction because they are correlated metal, nearly at the threshold of a Mott transition. So that's why I was just wondering whether the interaction plays any role in the harmonic generation, although
it might very well be. I didn't know that. I didn't know enough about that. That it's highly correlated. So yeah, the modeling I done is quite naive and simple.
Right,
so
which follows the other solid models.
Yes, yes, and but it's even more simpler because here I don't really need to solve any sort of TDC because I start with population and the conduction band, and that never changes. It's just driven around, and there is also no scattering or anything like that. So it's extremely naive model and also simple.
Okay, Kabat, did you have a question?
Yeah, I had a question. Maybe this is jointly for Paul and Marina. So I noticed in the frequency column as a reference, each frequency line is a lot narrower than what you can get from the high harmonic generation. If that's a requirement for optical frequency references, the second part now is a question for Paul. Is there a way to make these high harmonic generation frequency columns narrower if you want to use them as a frequency reference?
Let me, I'm not sure if I understand completely, but let me talk around it and you can ask me again. So if I think of each comb line that comes from the coherent superposition of each pulse in the mode lock train going on for, well, very long time. And so the line width is the coherence between pulse after pulse after pulse after pulse in the frequency comb. And that's the line width that people measure in the comb, and that's the line width, I think, Marina mentioned, it can be down to, I think it can be down to almost to 10 to the 1 part in 10 to the 19 now, but maybe Marina can correct that. Now we make a whole lot of these lines simultaneously. And so, and if you think of those as one pulse, that's a broad bandwidth. But then when you think of that as coherently reproduced, pulse after pulse after pulse, that's where the line width comes. If we wish to have fewer lines simultaneously, only that, instead of that, then I would need a longer pulse to drive it. And in a way, in the end, we will probably wish to go from, a few cycle now, which we're sort of focused on being an attosecond group, to being something longer in the long run. But I think to start, I figure that's not our big issue. So we're still aiming with few cycle pulse, trying to drive it hard and trying to learn about titanium nitride and the ideas of nanoplasmonic devices and things like that. And then ultimately you have to focus down and try to get a narrow line with the thulium line or for VUV or whatever you want to do with it. So I don't know if that was a complete answer to your question, but ask again if it wasn't.
Yeah, that was my question. The second part of my question. The first part was if the narrow lines are a requirement. Maybe Marina could answer.
Yeah, so for metrological applications, the narrower the line is of individual comb tooth, the better your resolution. So usually what is done is you have this optical frequency standards, an optical, a clock that has a clock transition in the optical range. And you usually have an ultra stable laser stabilized to have extremely narrow line to probe this clock transition. And then you can take this laser and beat it with one of the frequency comb teeth. And you lock the comb, you lock the comb frequency, the absolute frequency of the comb tooth to this very narrow line with laser that is locked to the optical transition of the optical clock. And thus you achieve this extremely high stability and very narrow line with the comb, which, yeah, 10 to minus 19 after averaging of several hours is what it can be achieved in.
It's amazing how good these can be now.
Can I ask a follow-up question, I guess, to Marina on this? So imagine your fiber frequency comb has a frequency spacing of, say, 100 megahertz. So each line is separated from the adjacent line by the repetition rate, and then by controlling the phase slip between each pulse, you can extrapolate each frequency comb down to zero frequency, or some fractional offset. Now you multiply that, say, to the 11th harmonic by going through, say, magnesium oxide. So are the lines still separated by 100 megahertz? And is the carrier envelope phase still, has it been demonstrated the CEP is still preserved in the XUV spectrum?
So I don't know if that has been shown in the XUV spectrum, but the phase stability is preserved when you mix or multiply the frequency of the comb, when you mix comb harmonics together to generate higher frequencies, for example. That is preserved, and this is used. The combs have been used so a comb that is locked to an optical clock transition and provides an extremely stable reference frequency. Its wavelength, its different teeth can be mixed together to generate microwave frequency directly equivalent to the frequency that you need to drive cesium fountain, cesium atomic clock, which generates a second. And these experiments have been done, and they show the superior signal to noise of the measurement, because the local oscillator is now generated from extremely stable comb that is locked to this to the optical clock transition, which exceeds the stabilities of hydrogen masers that are typically used as local oscillators. So I expect that, and that I showed you the equation that connects the carrier envelope offset with the phase, with an offset phase, which is in the frequency domain. It's one equation that connects the two. So I expect that this will be preserved as well in the harmonics as well.
Okay, thanks. Andre Staude, you've got your camera on. You're still in the office, but no questions. No questions. Okay. Anybody else with?
Yeah. Can I ask a question?
Yeah. Is that Julio?
Yeah, it's me.
Okay. Yeah. Go ahead. We don't see you, but we hear
Big
you.
G.
Yeah, you better know. I've my hands full here. To Alexei, have you? I've been doing very similar work on the zone plates on NGO for good or worse, and now I cannot finish it since I'm moving. But my question to you is: have you thought of how to measure the focused XUV? I mean, this is a very high NA focusing, so I assume you'll need some sort of near field spatial measurement or anything like that.
Yeah, that's an excellent question. I have thought about maybe if you could damage something, well, but that doesn't sound, and then use AFM or other like high magnification microscope. Alternatively, if we can make it very stable and maybe do some sort of knife edge, or, but I'm not sure if that, okay, how easy that would be, because yeah, you need everything to be like stable on the scale of like 50 nanometers,
yeah,
or so.
Yeah. So maybe we can talk. Yep. I've designed a setup here, and I was just about to get it to work, but now I can't. Oh. So maybe we could talk and share ideas of.
Yeah, that would be wonderful.
Okay.
Julio, did I hear another question coming from your microphone?
Yeah, my son asked me if this is my circle time. Oh, and here is the camera. It's upside down. I don't know why the camera. Yeah, stop. Okay, no more questions for me.
Okay. If not, I think let's call this to an end, and I will applaud on behalf of the audience. Thank our three speakers, and we'll be back next Friday. Bye-bye.
Thank you very much.
Thank you.
Goodbye.